Okay. All right. Okay, good deal. Okay. Well, morning. Thanks for being here for the Monday lecture. We're going to continue to talk about the column design. And after that, we'll go over the homework. I guess a lot of students have problem with the homework. And
it's mine.
We'll go over how we calculate the moment in details. Okay. And also, we only have one lecture left from the development lens, which will be finished on Wednesday. So mostly we'll have a review session coming up on Thursday, where I will go over the possible problem that will be included in the final exam, and also answer some questions if you have any. Okay, so that's the plan right now. And also I have to remind everyone that the online review CET evaluation score is open now, so please fill it. I really appreciate it because we have a requirement for you guys to fill it. And I'll also leave some extra time, say on Wednesday or Thursday, for you guys to fill it online. Okay, so that'll be that. So let's get started in our column design. Okay, so quick review. Excuse me. So quick review what we have done, right? So on the column design, there are two type of columns we're dealing with, right? So short column and slender column. So mostly we're dealing with short columns, right? Short columns, right? So columns design had two parts, the axial forces and the bending moment, right? And we talk about usually the bending moment is caused by eccentricity, right? So as shown here in this figure, let me share my screen, okay? Share my screen. Okay, so here we go. So first of all, we talk about the compression of the columns, right? Compression of the column. That's not hard at all. So if it's just a pure compression, we simply take the compressive strain, set them to be equal for both the concrete and steel, right? And we'll proceed with the calculation. That's 0.85 F prime C AG, which is a gross moment as a gross area, minus the reinforcement, plus the yield strength Fy multiplied by the reinforcement AST. Okay. Oh yeah. So the homework, Byron has to clarify that. Plus, again, there are two homeworks left. One is this one supposed to be due today on Monday, but since a lot of us have some issues, I'll go over it, and there will be a new deadline for it. It will be this Thursday. And this homework will be graded. And the homework will not be graded for the column design, which I will leave the homework this Thursday. And I also post the solution to that homework. And when I upload the homework, you notice there will be a no due date on the homework 9. That's right, Mason. Homework 8 is due Thursday. I'll send an email right afterwards, okay? Right after our lecture this morning. So let me say this again. Homework 8 is due this Thursday still. Homework 9, which is on column design, will not be due, okay? I will remove the due date from that homework, okay? Please expect to see that, all right? So quickly coming back. So we talk about the compression of the column, and we know that the compression can be taken upon by both the concrete and steel. And this is the equation for it, and there's a 0.85 reduction factor for the concrete, and we use the yield strength of steel for the compression of the steel reinforcement, right? And the most important thing is the interaction diagram, right? The corresponding force moment diagram. And we talk about how the moment can be generated by forces, by axial forces. It's due to eccentricity, right? Eccentricity. And this is the stress state caused by the eccentricity, right? So we have a compression P, we have a combined moment M, which equal to PE. So the combined stress equal to a uniform compressive stress and a tensile compressive stress distribution caused by the moment. Right? And we also realize that whenever the compressive stress reaches the concrete failure stress, it busts the column, right? It busts the column. So we use the interaction diagram coming from this stress equation. So I'm going to use a red, circuit out this stress equation right here. Okay? So that equation stays. But the problem is that here, well, not the problem, but here for simplicity, we assume the materials is linearly elastic. Okay. Yes. The final page, the final is on 12th. Okay. Is on the 12th, 10 a.m. Okay. I double checked the exam calendar, so it is 10 a.m. Okay. We're going to follow that. All right. So this interaction diagram. diagram right here. That is because we assume the materials is linearly elastic. I say this again, okay, I cannot stress enough. This is linearly elastic, okay? We use this diagram for illustration, okay? We use this diagram for illustration. When I keep repeating it, means in the exam, we have a problem like this, right? I draw the conceptual plot and ask you, okay, is this the shape of a column, right? Is the shape for the interaction diagram, right? You can find the answer for that, right? So the real, excuse me, the real interaction diagram for the column, right, has to take account the nonlinearity or nonlinear response of the concrete itself, right? So we have to consider the concrete stress response and recompute. Now, the compressive side is actually easy, right? So we have this CC, which is the compression from the concrete, and CS, which is the compression from the compressive reinforcement. And that gave us the total compression. Right? And then we have the moment. Right? And the moment is basically the force, sum the force with respect to the center of the section, okay? So I'm just gonna draw here in case you're confused, with respect to the center of the section. Okay, we're summing the moment here, right in the middle of the section, right? Right in the middle of the section, okay? So this is the, well, this is a set of equation how we use to calculate the axial force at the bending moment, right? But to complete the diagram, to complete the interaction diagram, there are several critical points. Right? So if we draw the x-axis, horizontal axis, set it as a bending moment Mn, and we draw the y-axis, set it as axial force Pn, and we could have a critical points drawn out on this curve. First critical point on the left would be a pure axial load. That means there's no bending moment or eccentricity equal to 0. So I can write here E equal to 0, right? E equal to 0. So in this case, I have pure axial force. I can calculate that point, okay? And go on, I have a point B, which is point of zero tension, right? And by the name of zero tension means if I go to this small figure here, means the maximum tensile stress is 0. There's no tension. Right? In this section. So we subsequently calculate this point B here, and we can reach the balance figure, right? Balance figure, where here's a C, right? Figure C here. Now, balance figure means, well, whenever my concrete reaches the compressive strength or failure strain, epsilon Cu, my strain in the steel reaches yield strain, epsilon Y. Now, remind us, right? Don't forget the yield strain for steel is 0.00207, right? 0.0207. And then we go on, we keep loading it, have more moment. As we have more moment, actually what happens is I have more strain in the steel, Now you realize that when I say more moment, that's not really appropriate, because in this curve here, when I come from C to D, my moment does not increase, my moment actually reduces. So I should say when you follow A, B, C, D, E, so I should write here A, B, C, D, E. This path is actually increased curvature, increased bending curvature, okay, bending curvature. So strictly since if this is a strain diagram, so I write here, this is strain diagram, and you should see A from this to B from a triangle, from C a balance failure, so both sides. For D, I have a little more in the tension, and for E, almost pure tension. Okay, so to help you remember, this will be a nice short cartoon for you to put your head, right? Put in your head so you can remember it. Okay, so it's all about strain. As I going from A to E, I'm basically increasing the tension side of it. Okay, so that's the trajectory of these critical points. Okay. So circle back, we have to mention that point D is tension control limit. Means the strain still reaches 0.005. And then the last but not least, compression zone, right? So it's a small compression zone. And we talk about this shortly, but this just means the whole section takes more attention, right? So when your eccentricity almost approaches infinity. Now, these are the concept of interaction diagram. So we showed example from last lecture, right? First point, we want to find the balance failure, right? And then second point, we want to find the tension failure region. any representative points, right? And then the third point is in the compression failure region, and the last point is the pure axial load. So we gone through the first one, where we set the compressive strain in the concrete equal to epsilon Cu, and we set the tensile strain of the steel equal to the yield strain, and then we proceed with the calculation, find out the total force and the moment, total force and the moment, okay? And then the second point, we simply set the strain equal to 0.0075, which is much bigger than the tension limit, 0.005. And then we proceed the calculation, find out the axial force, which is P, and we find the moment, which is M here, 238, okay? So these are the 2 points mentioned before, right? Now let's go on for the third point, right? Let's go on for the third point. So point 3, right? So this is a very small compressive zone, very small compressive zone, okay? So what does it mean, right? What does it really mean when I say very small compressive zone? That basically says, if I want to have a very small compressive zone, all I need to do is I want to make sure my C, which is the compressive zone size, let me write down here. So compressive zone size, you know that already, but just in case. And this, right, we want it to be much, much bigger than CB, which is C at balance failure. Okay, we want a compressive zone, actual compressive zone, much bigger than the balanced failure, Okay, so balanced failure. Okay, so we don't really know. Right? So we don't have an idea what is appropriate C to select. So let's go back to take a look at the section, right? Let's go back and take a look at the section. Now, my section looks like here, okay? And notice that my section has a height h equal to 20 inches and depth equal to a 17.5 inch, right? 17.5 inch. Now that is quite a good number, So I started thinking, what if, right? What if I set my compressive zone to be bigger than D, than the depth, okay? To be bigger than D, that's ought to be enough, right? That ought to be enough. So this is approximately 17.5 inch, right? 17.5 inch. So let's set C equal to 18 inch. Okay, 18 inch. So this way I ensure I have a very large compressive zone, right? Very large compressive zone. Okay. So what happens, right? If I have a compression failure. So I think I got it wrong here. So this is a compression failure. So large compressive zone. Compression failure. Okay. Okay, I think I got it wrong here. Okay, this is large compressive zone. Okay, this is large compressive zone, compression failure. Okay, so I set a large compressive zone, proceed. Now A, the actual compressive zone equal to 0.85 multiplied by C, which is 18. So I have a 15.3 inches. Okay, so that's my actual compressive zone. So the total compression force by concrete CC, equal to a 0.85. 0.85 now, the 4 KSI concrete, and then this is the A, just in case you forgot these parameters, and then last is the width B here. So this equals to 624 kips. Okay, so that's the compression force by concrete. Okay, now this is just the pure concrete compression force. I need to consider the steel. Okay, so in steel, I have Fs prime equal to Es multiplied by epsilon S prime, and that equal to 0.003. Well, let me back out a little bit. This is maybe a little bit too fast. So we call epsilon S prime is the compressive strain in the concrete. Sorry, in the steel. Right, so if this is a section, And my bending moment, say, is going this way. So we're talking about, let me circle out these fellow here, okay? These fellow here, all right? So now this has to compute it first, and I can compute that. That equal to what? Epsilon s prime equal to epsilon cu multiplied by a depth. Well, actually, in this case, this is compression. So C, sorry, C, small c minus a, sorry, minus ds prime, which is the concrete cover, ds prime, concrete cover, and then divided by C. Okay, divided by C. Okay, so that's the strain. And ES, of course, equal to a 29,000 KSI. Okay, so plug these numbers in. So Fs prime essentially equal to 0.003. C here case is 18 inches minus 2.5 divided by 18. Okay, and multiplied by 29,000 KSI. So I got this number to be 75 KSI, which is bigger than the yield strength of 60 KSI. Okay, so this is Fy. Now that's bigger. Now that's bigger. Okay, so what happens if it's bigger than the yield strength? We say this, okay, won't work because the 75 too big, exceed the yield strength, which is going to set the limit to be 60 KSI. Okay, set the limit to be 60 KSI. Okay, and then let's talk about the tension. Let's talk about the tension, right? The tension strain epsilon s equal to epsilon cu here on the top, which is d minus c divided by a c by 29,000. So ES. Okay, and I realized that after calculation, oh, sorry, this is strain. I realized that after calculation, my stress equal to ES multiplied by epsilon s. Okay, so this it gives me a minus 2 KSI. Okay, minus 2 KSI. Okay, what does it mean? This means, let me use red here so you can see better, means tension reinforcement. Supposedly the tension reinforcement will take care of tension, now cease compression. Okay, so this means entire section bears compression. Entire section bears compression. Okay, so that means now I have a large enough compression zone, the entire section sees compression. So I'm satisfied. So okay. So this is in the compression region. This is the compression region. Now you ask in the exam, if this does not see compression, what will happen, right? If this does not see compression, what happened? So we have to go back. If this is not the case, we have to go back and increase C, right? Increase the compression zone size to see the entire section under compression, Okay. Okay, so this is the case, right? This is the case. Okay, now let's proceed with it, right? So this is the tension, this is the compression. So now I want to calculate my total force, right? So P, total force, equal to Cc plus Cs prime minus Cs. Okay, minus Cs. Okay. Okay, be careful, okay? Be careful a little bit, okay? All right, so what is the CCCI? So CC here, the total compression force from the concrete, I just calculated out 624, right? So before, let me write it even out. So CC plus, this should be Fs prime multiplied by As prime minus Fs multiplied by As, okay? And now I have 624 plus 60 multiplied by As prime by my section. Let me take a look. As prime from my section. For number 9, so I get 2 inches squared, right? 2 inches squared. So here I get 2 inches squared and minus Fs, we just calculate this, minus 2 and 2 inches squared. 2 inches squared. Okay, so I got a total number to be 748 kips. 748 kips. Now I still want a moment. I still want a moment, right? So I will calculate moment the same way as I did before. So m equal to first, this is 624. Distance here now is half h, which is 10 inches, minus 7.65, which is half a, right? Half a. So this is a divided by half. If you forgot this formula, you can refer to the previous formula right here, okay? Previous formula right here, okay? So, and then this is 120, and the distance is half h, which is 10, minus 2.5. This is the half cover, and minus 4, 17.5, which is d, minus half h, which is 10, okay? And this whole thing divided by 12, so I switch from inch to kips to foot. So eventually I got a total moment m equal to 195 kip feet. Okay, so quickly I can calculate my eccentricity E equal to 195 kips feet. Let's convert back to inches multiplied by 12 divided by 748, which is the axial force. And that gives me a 3.12 inches. Okay, so this is the represented point in the compressive failure zone. So let's proceed. Now, last point is assuming I have pure axial load, pure compression. Pure compression. Okay, so for pure compression, for the case of that, I want my C, total compressive zone, equal to infinity. Infinitely large compressive zone, and I don't want to have any eccentricity, so E equal to 0. So in this case, I recover my original compression equation, 0.85 F prime C AG minus AST plus FY AST. Okay, I bring a number, this is 0.85, and this is 4, and this is 12 multiplied by 20, total area minus 4, and plus 60. 4, and this gives me 1,042 kips. Okay, so summarizing all these data, I now have my own interaction diagram. Okay, so what it looks like. So I have my my y-axis as my force Pn in terms of kips.
Oh, excuse me. Oh, what is that up there? It's FC times AY minus A. What is that? A something T? Just like 3 lines above where you were.
I know. Remember this equation, Sean, where we see the pure axial force?
Oh, AST. Oh, okay, there it is.
You understand the steel, right? ST represents steel, right?
Okay, yeah, I just couldn't see what exactly that was. It was a little bit scribbly.
Okay, well, I can clean up for us. So
Sorry.
That's all right. But you shouldn't feel strange about this equation. This is a very basic equation we use for axial forces. Okay, so in the exam, you want to actually remember this equation. Okay, this is a very important equation for axial forces. What I mean by that is if all failed, run out of time, at least compute these axial forces. Okay, at least compute that. All right. Okay. So getting back to where I was talking about. So the moment at n here, I want to keep the unit to be kip feet. All right. So this is my axis. Okay. Now let me start drawing some points. Okay. First, I have my pure loading here. P0 equal to 1,056 kip. Okay. Kip. There's no feet here. Just kip. Okay. And then I start doing my next point, right? Next point is the large compressive zone region, right? So Pn equal to 748 kips. This is C, okay? So let me label it so you see better. So this is basically 4.3. Okay, so this Mn equal to 195 kip feet. Okay, where I have my balance failure, right? So the tip of the interaction diagram here, Pn equal to 357 kips, and Mn equal to 317 kip feet. Okay, and circle back right here, I have my axial force Pn equal to, let me check real quick, that should be my 0.2. So 133 and 238. So 133 kips, 238 kip feet. Okay. All right. So these are all my points. These are all my points. Okay. Now, how do I get the interaction diagram? Before I do that, right? Before I do that, let me label all the eccentricity. So this is 0.2. This is 0.1. Okay. So let me label the eccentricity. So eccentricity here, in this case, E equal to 0. Okay, so I connect this line here. This is E equal to 3.12. Okay. And this is here, E equal to 10.66. Okay, and this is here, E equal to 20.83. Yep, 20.83. Okay, and then of course this is E equal to infinity, but we don't have a point there. Okay, so now when I draw my interaction diagram, I simply need to draw this diagram together like this. Okay, I have it. I have it. In the exam, okay, so what are the key points we're looking for in the exam? In the exam, we definitely look for this balance failure. So you need to draw 0.2 for sure. We also need to draw the pure compression. Okay. And then once you have this point locked, 1, 2, all you need to do is pick a point here. And usually we can set this to be 0.0075. Okay. And this point we set compressor zone C for the concrete. Clean this up a little bit. C equal to bigger or equal to D, which is depth. Don't really like this. Try to do it again. C bigger or equal than D. Okay, so this point here. All you need to do is draw these 4 points. Once you have these 4 points, you can finish the interaction diagram. Okay, all right, so this is what we need to do for column. This is all there is for column. Okay, of course, there are more for column design. In this course, we're not going to dig too much, okay, because we have a column design. There are some details with the rebar geometries and everything else, right? Rebar geometries and everything else. So we're not going to dig so much. We're not going to dig too much, okay? But just give you a basic idea how to do column design, okay? All right, so that's it for the column design. Any questions on this, on column design? Any questions on column design? Okay, this is very detailed information. I'm pretty sure you need a lot of time to digest. And in the exam, you will be required to solve at least one problem on column design, right? On column basic interaction diagram. So problem like this. So please do go through it, okay? Please do go through it. If you have any questions, please let me know, okay? If you have any question, please let me know, all right? Okay, so I'm gonna pause a little bit on this and then come back. So first of all, let me open up a new slide. Okay, so let's talk about homework. Okay, let me see if I can share the screen of the homework. Okay, homework. Oh, here we go. Homework, where are we? All right, just give me a second. Okay, homework 8. All right, okay. All right, so how do I give this to my notes? All right, well, I think I can do without it. All right. So guys, if you have your PDF file, please open it up. If you don't, that's okay. I'm just gonna draw it out for you. Draw it out for you. Okay. Now, I know you have a lot of questions about homework, especially the first problem, right? The quick thing is you don't know what to do, right? You don't know what to do, where to start. Now, if you look at our lecture notes, if you look at our lecture notes, right, we have talked about this in the lectures, okay, where we're given a T section like this, just like this, we're given a T section, okay? But we didn't draw out the reinforcement. That was the thing. We didn't draw out the reinforcement, okay? And we also talked about how to convert the section, right? How to convert steel to concrete, right? So for the IGT, gross moment inertia transformed, we need to convert the steel, which is right here, and the compression zone. Okay, in the homework, this is file number 8 bars. Okay, we need to convert this to additional concrete, right? So it will be like this. And you can clean them up, remove them, okay, by adding a little bit of wing to it, and this will be N minus 1 AS, N minus 1 AS, okay? Okay, now you have the bottom here, bottom here, and this, let's say this is 7 number 8 bars, okay? To convert that, right, we need additional wings here, Now remember for tension, when we said before, when it's cracked, you do NAS directly, right? You do NAS directly, but this is for gross, right? This is total, means this is uncracked. Okay, this is uncracked. When it's uncracked, you convert everything. So this is, again, you got to fill back in the reinforcement, and this is N minus 1 AS. Okay, be careful, this is uncracked. So you have the entire section to work with. Okay, so how you do IGT? You find a neutral axis, okay? You find a neutral axis, you proceed with the moment inertia. Okay, so that's how you find IGT. But this is only for positive bending moment. Okay, positive bending moment. Now some of you ask, how about negative, right? How about negative? Okay, so think of a little bit, okay? Now we're talking about uncracked. Okay, so when I talk about positive and negative bending moment, I'm talking about either to flip the section or not to flip the section. All right, but the question is, do you think the neutral axis will change if you flip or not flip the section? The answer is no, it will not change. Okay, so you just flip the section and you do the moment inertia for the full section again. Okay, and this is for uncracked. Okay, this is for, oh. My screen zoomed in far past the diagram. Okay. All right, let me stop sharing a little bit. So let me see here. Okay. All right, can you guys see better? Okay. So this is for the uncracked section, okay? This is uncracked section, okay? So be careful. This is slightly different from the lecture notes. The lecture is IG, okay? And this is asking you to do IGT, okay? Now for the cracked, so this is uncracked, okay? This is uncracked. For cracked, things a little bit different. For cracked, things a little bit different. When it's cracked, I have to differentiate between positive and negative. So it's positive, I have to take the top bar, get it out, because the top bar will be in a compression zone, so this is N minus 1 AS. And bottom bar will give an equivalent area of N AS only, and don't consider the concrete anymore because it's cracked. Okay, so in this case, you find the compressive zone either within the flange, let me use a different color, either within the flange, something like that, and you proceed to go on to calculate moment inertia. Okay, and please see the notes. So for the also for the cracked, but negative bending moment, right? And you flip the section, okay? You flip the section. So essentially, top bottom here, you still see compression. Still see compression. So, because I flipped, right? I flipped the sign. So somewhere here will be the compressive zone. Somewhere here will be compressive zone, and then you convert to the steel to concrete by N minus 1 AS. Okay, and here will be the top bar, but now in tension, and this is NAS. Okay, you flip section and calculate the moment inertia this way. Okay, all right. Now, once you've done that, right? Once you've done that, then you can solve the problem. Okay, all right. I hope I'm clear on how to solve this. Now, if you have more questions, I will be there Tuesday, 2 o'clock. Okay, to answer any questions. Okay, I'll be here Tuesday, tomorrow, 2 o'clock. Neutral acid for the cracking moment of inertia, right? So remember in the lecture notes, right? How do we do it? Right? If you go back to the lecture note, how do we do it? Right? So we need to find a Y bar, right? We need to find a Y bar, right? And this Y bar, remember we use rho and we use KD. Remember K? So from lectures before, right? From lectures before, okay? Several lectures back when we talk about transformed moment inertia, right? Serviceability, does that ring the bell? Cracked moment inertia, right? So let me see if I can find it. Okay, so I think I might have done this earlier, okay. Can you see this? You see this? So this is how we found one top. This is uncracked, okay? Be careful, this is uncracked. So for cracked, right? For cracked. Okay, this is where you find it, okay? Okay, now trick is for T section, for the section like this, for it's cracked, the compressive zone mostly is in a flange. It's in the flange, right? So you can use the same equation to treat it as a rectangular section. Okay, treat it as a rectangular section. Okay, all right. Any other questions? Any other questions? Any other question on this? All right, well, if you have no other questions, let's work on it a little bit, and I'll see you tomorrow, Tuesday, 2 o'clock in the afternoon. I used the link before, and if you have any questions, I can answer your question there as well, okay? We can have a detailed conversation then, okay?
Hi, sorry. Can I ask one question?
Yeah, please.
Yeah, so like if we were to use KD, in order to find rho, we use AS is equal, we use rho is equal to AS over D times B. So like for this problem, I think I tried doing that and I ended up getting
which area you use? Do you use BF or BW?
For the area, I think I used the bottom flange.
Well, use the top flange and you have a wider, right?
Yeah. Right. Yeah. So that's that. Yeah. I used the B for the flange.
Right.
And then the D that I used was the D down to the tension reinforcement.
Mm-hmm.
After doing all that, I think I ended up getting a KD that was something like 7.83. So it was greater than the HF, the H of the plan.
Mm-hmm. I see. Okay. So here's what you do, right? So the question is where this equation coming from, right? So how do we get this equation? So if, let me just write down here, maybe it's better, right? So you took mechanics materials, right?
Yes.
Okay, good. Okay, that's good. So now, this is the T section, assuming this is 6 inches. I haven't done the calculation with that number you get from homework exactly, because I changed the number slightly. But as you're saying, assume you're right, and then your compressive zone is estimated right here, right?
Right.
Okay, so we can do this. You know this already, this top area, okay? And let's call it 1, and let's call it part 2.
Okay.
And then for the sake of argument, I am not going to include this little wing part, which is actually from the compressor reinforcement, right? So this, let's call it 3. All right, so you can include it, okay? But all I'm saying is you have a crack section and you don't know where the neutral axis is.
Yep.
That's the question, right? And this is the bottom reinforcement right here, right? So this is calculated already, and you know this is NAS.
Right.
Okay, so assuming I have a distance, right? Hold on, this is, okay. So assuming I have a distance of the neutral axis, y top distance away from the top fiber, okay? And this is where I want to find out, right? This is the question, right? This is the answer to the question, right?
Yep.
Okay, so what I do is this. So I want to find out the center of the first piece, right? Because now this equation should satisfy this, is that when I have everything said and done, right? The total sigma AI yi should equal to 0.
Okay.
Right? Remember this, right? From mechanics materials, right?
Yes.
Okay, so to proceed to calculate that, piece 1, right? A1, so I want to list the table here, A1, right? AI, yi, and AI multiple yi. And this is number label. So I make a little bit table, tiny table here. So part 1, right? So this is I dot. So part 1, AI is, say this is the BF on the top, right? So BF multiplied by HF.
Okay. Yep.
Now the distance would be HF divided by 2, which is this distance, right?
Yes.
And plus this distance, right?
Mm-hmm.
Right, so it will be HF divided by 2 plus Y top minus HF.
Okay.
Okay, so this here would be BF, HF, then, you know, just multiply these two, right?
Right.
Okay, so I'm going to save that. And then 2 here, right? So the area of that will be, this is BW now, right?
Yep.
Width of the web, right? BW, right? Okay, now I'm talking about 2 here, okay? This tiny part, use it.
Right.
Can you see it? Can you see my
Yes.
screen? Okay, good.
Mm-hmm.
So now I'm going to use BW, which is the width, and multiply by Y top minus HF. Right? Right.
Mm-hmm.
Okay. So the distance will be Y top minus HF divided by 2.
Mm-hmm.
Okay. So these just multiply them together, right?
Okay.
Right. Now I have 3, which is the top wing part, right? This wing part, and we know this is N minus 1 AS.
Mm-hmm. Yes.
right? So this is n minus 1 as. And the distance will be what? Say, here I have the concrete cover of ds prime, right?
Yes.
Okay, so there will be y top minus ds prime.
Okay.
Okay, and then this will be 2 multiplied together, right?
Mm-hmm.
Okay, now don't forget we have the tension here, right? So this is number part 4, right? The reinforcement part.
Right.
Right, so don't forget that. So this is number 4, and the area of that is NAS, right?
Yep.
Okay, so the distance here would be what? I have a depth of total from top to bottom to the reinforcement here is D, right?
Right. Yep.
So the distance will be D minus y top.
Okay.
Okay, and now one thing, this for the tension is actually a negative distance. You understand why?
No.
Okay, so this is neutral axis, right?
Yep.
So on top of it, on the top of the neutral axis, y is positive. Below it will be negative. Okay.
Okay.
So since the rebar, which is R4 converted, is at the bottom here, so that will be negative.
All right.
Okay, and this should be covering the mechanics of the curve.
Okay. So I just want to make sure I'm not crazy then. So for the rho, rho is equal to AS over B times T.
Yes.
And the AS we're using is the one in the
tension side, always in the tension side.
Okay, then yeah, that's
right.
What you do is
the idea, I understand you're not crazy, okay? The idea of using that equation is approximation, because if you use that equation, you're basically assuming everything is going to be in the flange zone and in the compression, and sorry, the compression is in the flange, and you can treat it as a rectangular section.
Okay, yeah.
Right, but it turns out it's not the case. Then you have to do the full-blown analysis.
Okay, yeah.
Right.
That helps. I just wasn't sure. I mean, I wanted to do it that way.
I understand. Okay, I didn't know you guys end up exceeding the flange because I changed the number slightly, and that might disturb the game a little bit.
Okay, thank you.
Yeah, no problem. Is this clear? Better? Is this better now?
Yes.
Okay, good. Okay, so I'm gonna upload this part as well to the to the canvas. Okay, so you guys can see it. But I think this is the mechanics materials content. Okay. This should be covered in the mechanics.
Or something about writing a journal.
I'm sorry. For that area down there before the n times the AS, you said that was like there was a negative distance to the neutral axis.
Yes. So let me circle it out. You can see better. Here, can you see it? So this is the negative you're talking about, right?
Yeah.
Right. So this comes from mechanics materials class. When we say a neutral axis, this is my blue blue line here. This is my neutral axis, right? Can you see it?
So that subtracts away from your total moment of inertia for the crack section?
No, Sean. Try to see from my label system here. See, you have a yi, right? Can
yes.
you see my? Okay. This is defined as the distance from the center of this area to the neutral axis, right?
Right.
And then when we define the distance, right, from center of this area to neutral axis, we set neutral axis as 0 point, and the compression zone, which is the top, this is positive sign, distance-wise, okay? And this is negative sign. Okay, that's just the how definition, how it was defined, okay? Got it?
I think so.
Okay, so the negative sign here is just by definition, all right? So D minus Y top is positive, right? It's a distance, right? It carries a sign because on the negative side of the neutral axis. Okay, if you're still confused about the sign system, positive, negative, you can dust up your mechanics materials lecture notes and see from there. Now, if you're still not clear about it, we can discuss again tomorrow, Tuesday at 2 o'clock. Does that help, Sean?
I guess we'll see.
Okay, well, this is the typical sign when we do, because you have to make sure your total add up summation AIY equal to 0, right? Can you see this equation, Sean?
Yes.
Okay, so if one is 0 and everything is positive, there's no way the balance to become 0, right? Right, everything is positive here, right? So there's got to be one term at least is negative, right? And by definition, it's the distance, which on the other side of neutral axis and tension side of neutral axis will be 0, will be negative. So the equation can eventually balance out to be 0, right?
Okay, yeah, I'll just have to.
Okay.
Just
Okay.
have to
Well,
look at it more.
do a little bit of homework and you can see what's going on. Okay. If you're still not clear, we can discuss more tomorrow at 2 o'clock. Okay. All right. Okay. Any other question about this? About how it's due tonight? No, Justin, the homework is due on Thursday. Send the email out. Okay. So we extend the homework deadline. All right. On this. Okay. All right. Sure. No problem. Anything else, folks? Okay. I gotta stop. It's 10:15 now. I have send the email. I will send the email about homework. But do let me know if you have any question on this, because I'm pretty sure you have a problem in exam just like this. Okay. So do let me know. All right. Okay. I'm gonna stop here, and I'll meet you guys again tomorrow at 2 o'clock. Okay. Appreciate it. All right. See you guys.